A dilation is simply scaling an image upwards or downwards but keeping the shape the same. Or essentially, it's the transformation in which we can change one figure to a similar figure. So recapping back the last chapter, remember the key concept behind similar figure is, number one, all of the angles, if it's a polygon, must remain the same. And number two is that all the sides must be proportional to the original figure, assuming you're using the respective side. So like if you have side A, B, C, the sides on the new triangle ABC must be proportional. So you'd have like A is to B equal A prime is to B prime, and so forth. But like, let's look at an example, and I wanted to show you how you can do a dilation under using dot paper. And moving back to the slides, it gives us some of the key definitions and ideas that can help us understand how to perform a dilation. And kind of like with a rotation, remember that what I said is the key component of a rotation is the center, where because it depends on where you're starting as to what the image will look like. Because if I rotate a triangle about its center or its center of mass, it might rotate like that. But if I rotate it about a different point, I can kind of imagine it rotating about a record player, and so it should have the same shape, but the location will actually change where it ends up. And the same is true for dilations. If you're say you wanted to, again, it's kind of like creating a larger or smaller figure. Sometimes we use the phrasing stretching or skewing or shrinking or blowing it up, shrinking it down. All those sorts of things reflect the idea of what a dilation does. But let's go ahead and look at the definition of a dilation. And as you can see in the graph from our textbook, a dilation is kind of like, say we had the original triangle ABC or ACB, the larger one A prime, B prime, C prime, or A apostrophe, B apostrophe, C apostrophe, we would have a larger triangle like this. And if you look at it, notice that, well, the first, AC was length 3, here AC is length 6. I can tell that it's double the length. And every other side must also be double the length. Because if it's similar, it must be proportional. And another key about a construction, again, if you were to do a construction of a dilation using just a compass and no rulers, no grids, no Cartesian coordinate system, the key is keeping each line from the original point to the dilation point, the center of the dilation, to the new point collinear, meaning along the same line. So essentially you would connect each point to the center, and then you would extend the new points along that line. So since this dilation has, we'd say, a scale factor of 2, remember that scale factor just means the like the constant of similarity based on the proportion. What is it being multiplied or divided by to increase or decrease the scale? Notice that we're just doubling the length away from that in order to apply a scale factor of 2. And let's say you wanted to shrink it down by a factor of 1/2. What you would do is you'd take each of those 3 lines that connect the center of the dilation to the point and cut them in half instead. So you could use a bisector method if using a compass, or again, using a compass in a straight edge, you would just extend it and use the compass you could trace out a circle, or just, copy a congruent line segment. Or if you wanted to triple the length, you would just do that and then do it again, and, just kind of extend lines in that sort of manner. But if we look at the definition of a dilation, and I forgot to mention the term collinear is just, we have to make sure that it's along the same line in order to properly expand the dilation. So a dilation from the plane to a plane with center O and a scale factor r is greater than 0 is a transformation that assigns each point to a new point such that OA and A apostrophe are collinear. O is not between them, and OA is equal to ROA, where that's basically the scale factor, meaning that the new length is equal to the multiplier. So, like, let's say we wanted a scale factor of 1/2. That would just mean the new new OA is half the size of the original OA. Or like in this case, we have a scale factor of 2 because it's double the size, which is why the original OA, the new OA is twice the original OA. And Theorem 13-2 says that under a dilation, the image of a polygon is similar. And remember, that's really the idea of what we're doing, is to create the same shape, but larger or smaller. And that's always, it will be similar, again, assuming that the angles have been properly preserved and the sides are proportional. And again, the term isometry, which is a term I mentioned a lot in class last week. Sorry, I got distracted by some things going on with my dog. Is that when we keep a figure the exact same size, or when we move it, when we apply a transformation to it, like say for example a translation, a rotation, a reflection, or even a dilation, all those are called transformations. And the idea of similarity is that we can perform such transformations to them in order to get from one place to the other. And remember, the term isometry is just like the term of a translation or transformation, where we're taking one image and changing it using those steps. But anyways, let's get back to an actual example. So number 8 in our note says, find the image of ABC under a dilation with center Z and scale factor 2. And then let's also go for a scale factor of 1/2 just to compare those. So right off the bat, again, the center is an important part. Like what I'm imagining here is we have a triangle. It's going to be getting larger. And, we've been using this triangle, the same shape, to do a whole lot of different stuff. But basically what you want to, what it should look like is that you can see, well, the sort of the X to Y components between A and B is sort of 2 to 1. Well, that should double to 4 to 2 if you're thinking about how this will be if we were to just double it. Or again, you can kind of think about measuring this and just doubling its length, and doubling the length. If you double each of their lengths, that should give you a similar triangle with a scale factor of 2. However, a dilation specifically has a center, and that's kind of the key way of figuring out, well, where will it actually be? Where will the image of my of this transformation end up? But again, it's kind of like if we think about, well, how far it is from the center. In this case, here's ZA. Well, ZA prime should be double the length of ZA. And it should be collinear. So if I take it along the same line and I just double that length, this should be the location of A apostrophe under that dilation. And again, you would continue that procedure to do this for the other points as well. So AB is, again, we can kind of use the dots to help us. As I was saying in class, the dots are very helpful. Here we have 3 to 2. Well, I would just need to double that. 3 to 2 would give me the point for where B apostrophe would be. But again, if you were thinking about this using a straight edge and a compass, we could take this length, connect those 2 points using the straight edge, and then extend a line going further. Then we could use the compass to measure that arc, and then place our compass here, and then create an arc there of equal length using, not moving the radius of the compass in order to find out where our B prime would be as well. But it's quite a bit easier if you use the techniques of the dot paper, and same thing with Cartesian coordinate system. You could use those sorts of measurements as well. Anyways, and then with point C, thinking about, well, how far is it from Z to C, and then doubling that length. Well, here we have 1 down and 1, 2, 3, 4 to the right. So I would just duplicate that again. 1 down, 1, 2, 3, 4 to the right. So give me C apostrophe. And then if I were to connect those points, let me actually use, I'm not going to try to draw these because I can't draw things very straight. Whoa, that is not what I meant to do. Let's undo that. I was assuming this was going to give a straight line, but apparently not. I think this is interesting. Well, apparently this is not a straight line tool. Maybe this one will be the straight line tool. Also no. All right, I give up with that. I'll just try to draw it. But, you get the idea. If we were to connect those with the best straight line that I can, this would give us the image of our triangle under a dilation. And again, we're assuming that it will be similar to the original. And I'm trying, sorry, let me get this last point, do my best to connect those together. Good enough. And again, we could say, well, what are those lengths? Again, we haven't really talked about how do we measure the lengths of these sorts of components yet, but by the Pythagorean theorem, we could see that this length will be double that as well. And assuming we've correctly applied the construction of a dilation, it should 100% prove it should be proven to be similar, meaning all of those angles will have to be the same, and all those lengths will have to be proportional by a factor of the scale factor. And again, the scale factor is just like, well, here, the original length, let's just say we call this L, and then the length of the new, since I duplicated that exactly there, of course, that would make 2L. And, let's say you were wondering, what if I wanted to use a scale factor of 1.5 or 3.5, or that's the same, or 1/3 or something like that? Well, then, again, with the dot paper, it's not as convenient because it's good for doubling and halving and stuff like that. But, you can always do your best estimation to figure out those sorts of things. Like, say, for example, we wanted to dilate it 1/2 instead. Instead of doubling the length, we want to cut it in half. So again, kind of taking the same mindset, the distance from Z to A, we want to chop that exactly in half. And that will give us the location of, where would let's just call it a double apostrophe, for scaling it back by a factor of half or shrinking it. And same with A to B, we have the point from here to here. We want to go exactly halfway between. And you could use a bisector method to find that point quite easily, which would be somewhere about there-ish for B double apostrophe. And then C double apostrophe would be exactly halfway between the X and halfway between right there. And, we would get a... it doesn't really mesh with the dot paper, but you can still use your imagination to figure out how you would scale it by that sort of dilation. And, we often use the term shrinking for a dilation where its scale factor R is less than 1 because you're making it smaller instead of making it larger. And then a stretch or a magnify for when the scale factor is larger than 1 because it will make it bigger and bigger and bigger.